All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another great day in Calculus 2 class. We are going to be picking up where we left off last time. Last time we introduced a couple important concepts. Let me pull this guy up for you. So yeah, last time we looked at sequences and series. So just to jog your memory a little bit, a sequence is just a list in a definite order. So there's just a list of terms. For us, it's just going to be a list of numbers, and they're in a definite order. We can denote them by a letter with a subscript that indicates the position in the list that we're at currently. One thing that's important is knowing when a sequence converges. This just means taking the limit of the formula that gives us the terms. And if this goes to a real number, we say that the sequence converges. If it doesn't, we say that it diverges. We can visualize sequences as shown, and the limits of sequences, convergent sequence, actually has all these properties. This is what it meant for a sequence to decrease, and that's where we ended there. Sequences we really only needed for, they're important in general, but we really wanted to use them basically to understand series. And the series is just the sum of the terms of a sequence. So when you just take a list that's in a definite order and you start adding up all the terms, you get what you call a series. And of course, if the list is infinite, you get an infinite sum. And this idea of an infinite sum is what we started to explore last time. It turns out that every now and then you can add up an infinite number of things and you actually get a meaningful answer, as we did with figuring out the dichotomy paradox. We added an infinite number of things and we ended up with one was the answer. Whenever a series adds up to something meaningful like this, like it adds up to a real number in some meaningful way, specifically in this way that we defined, we say that the series converges. It's very different from saying the sequence converges. For a sequence to converge, we just have to check a limit. For a series to converge, the sequence of partial sums needs to converge, which means essentially we'd have to be able to find a formula for the sequence of partial sums and then figure out what that limit is. This is a little bit tedious and it can be quite difficult in general, so we're not going to be using that strategy. Today we're going to learn other ways to determine that series converge. But a series converging or diverging is very important. Series in general are very important, and we've actually seen applications of this before. The definite integral is in fact an infinite series, and it converges to the area under the curve whenever it's defined, the net area under the curve. One thing we looked at is that series can converge in two different kinds of ways. This is actually a very important idea. They can converge absolutely, and that just means you take the list, you put absolute values around all the terms of the list, and then you add those guys up. If you add up those terms, these new terms, the absolute values around the terms, we say that, and that makes sense as an answer, it gives you a real number, we say that the convergence is absolute, or the series converges absolutely. Now it's going to be possible that we're going to have a series that does converge when we add up the terms. It gives us a meaningful answer. However, if we put absolute values around all the terms and try to add it up, then it no longer gives us a meaningful answer. Whenever that occurs, we say that the series converges conditionally. It converges on the condition that we leave the absolute values off. So these are two different types of convergence, and it's actually very important for us to know the difference between these two, because there's something called the rearrangement theorem. The rearrangement theorem basically says, if a series converges conditionally, then you can rearrange the terms to get any sum you want, which means the sum is not going to be well defined. It's not going to be an entity that you can move around in a mathematical equation like you can move around a regular number. However, for a series that converges absolutely, then no matter how you rearrange the terms, you will always get the same answer. So commutativity of addition works. So this basically means that we can treat an absolutely convergent series almost like we can treat a number in any equation that we had before. It's a bona fide mathematical object that we can move around. We can distribute things across it. We can move it across equal signs. We can integrate each term. We can differentiate each term, and it's all going to work out. When a series is conditionally convergent, this is not true, because once you rearrange the terms, suddenly your answer is going to change. Suddenly the integral changes depending on what order you added the Riemann sums in, or whatever. So it's not good for calculus, and it's not good for a lot of other mathematical objects when we have a series that is conditionally convergent. So it's actually very important for us to tell the difference between the two. Another thing we looked at, and I just was looking at something like that.
So,
Another thing we
Jhevon, the
yes,
rearrangement theorem, like, it works only when it's like an absolutely converges, so not when it conditionally converges.
the rearrangement theorem says that if it's absolutely convergent, then all rearrangements give the same answer.
Yeah.
This is not true if it's conditionally convergent. So the conditionally convergent guys aren't as good in a lot of mathematical contexts. So absolutely convergence is the gold standard. That's the one where it's really nice and we can do a lot of things with it. Conditionally convergent, not so much. We then, and this was, we were sort of rushing at the end, so I guess I'll talk a little bit more about this specifically. We looked at the properties of convergent series. And we looked at two properties. There are two properties here, and here's a warning that says the third one does not work. So here's one thing, and we kind of also knew this from before in Calc 1 as well, but it's worth reminding you. For a series, you can always factor out a constant factor, a common term. So for example, if I'm looking at, if I had to illustrate one, if I have the series, say n goes from 1 to infinity of c times an, well, that just means ca1 plus ca2 plus ca3 plus going on forever. But c is a common term that I can factor out. And so what's left outside here is just the series of an. So you can factor constants in and out of series, and that's going to be useful in several contexts. Also, series distribute across sums. So if I have the sum of, say, an plus bn, then if I'm adding up these terms, it would look like a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus da da da. That's in red there because that's the warning. Let's give us a little more space. And so what can happen here? I can group all the a's together. Again, I'm going to maintain the same order because unless we have absolute convergence, things can mess up if I change the order. And then you'd realize that the first one is just the sum of the a's, and the second one is just the sum of the b's. And this can work out for whether I'm adding or subtracting sums. It means that you can group terms, and it works out mathematically as being that the series can distribute across the sums. Now, this reminds us of limits. We can factor constants outside of limits, and limits can distribute across sums, but that's pretty much where the similarity ends. Because here's something that would work with limits that exist, but it does not work with series. The series of a product is not the product of the series. Series do not distribute across products. So that's very important for you to know. So if you're doing some sort of mathematical operations, you should know that a series will not distribute across a product. In fact, if you were to look at this, if you take a series of an and then you multiply by a series of bn, this is going to be greater than or equal to the series of an, bn in general. More than likely, it's greater than. And why is that? Well, if you look at this guy, this is just a bunch of terms, A1B1 plus A2B2 plus A3B3 plus going on forever. Whereas if you look at this one, that's like A1 plus A2 plus A3 plus dot 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 times B1 plus B2 plus B3 plus dot dot dot. And then you start to expand the parentheses. So you're going to get A1, B1, and yeah, eventually you're going to get A2, B2, and eventually you're going to get A3, B3, but you'll realize that you'll get a bunch of other things as well. You'll also get A1, B2 plus A1, B3 plus going on forever. And you'd also get A2, I'm missing a B here, B2, A3, B3. And here I would get A2B1, and I would also get an A2B3 plus da da da. And I'll get here an A3B1 and an A3B2, and an A3B3 plus a bunch of other things. So you'll see that the left side here is actually much bigger than the right side in general. They're only going to be equal if either the AN or the BN are always 0. So this is not true. Series do not distribute across products. That's very important. So that's where it deviates from limits. Series are not as nice as limits. So you don't want to think of them the same way you do limits or a lot of other things. They distribute, you can factor constants out, they distribute across sums. In terms of nice little arithmetic tricks, that's pretty much it. Almost everything else, the series are going to be a lot more complicated to deal with. So that's worth mentioning. Now, normally at this point, I would introduce something called a telescoping series. But this is sort of an optional topic. I covered it with my class in the spring, but I'm not going to cover it here. So that's that. If you want to see that covered, you can watch the video from the spring. But for now, it's the summer. It's already cramped. It's already packed. So I'm going to kind of try to reduce all the optional topics that I cover. Well, no, I mean, if I'm not covering it, it wouldn't be fair for me to test you on it. So no. By the way, I'm not going to skip anything that you would be, remember, I'm not writing your final. So I'm also not going to skip anything that could potentially show up on your final. So telescoping series is not in the official syllabus. It's a very important kind of series, though, which is why I told my class about it in the spring. But in general, you're not technically required to know it. And there were some things that I told my class in the spring where technically they weren't expected to know, but I think it was nice for them to know anyway. I taught them an extra integration technique. I taught them about telescoping series and some other things that I'll be skipping for you guys because it's really too crammed. You don't have too much time to absorb everything. So it's I don't want to pack your brains with optional information. Okay, so yeah, so let's wrap up there. So now we are going into trying to figure out how can we tell that a series converge? As you can probably tell, series don't work as nice as limits. And so we probably can't use a very similar thing as we did with limits to determine when a series converges. It's a little bit harder to tell when a series converges. Potentially, it's a lot harder to tell when a series converges, right? So the next class and a half, we are going to be spending a lot of time just figuring out when series converge, how can we tell that they converge? And like I said, this is going to be easier than integration in general. However, the feel is kind of going to be very similar to integration. I'm going to teach you several techniques for which you can determine that a series is going to converge. And you are going to have to realize which technique do I apply to which series to make the determination. And of course, after I teach you all the tests, I'm going to tell you a strategy for these tests so you'll know when to try which one first or second or third. Pretty much the same thing that I did for integrals, I'm going to do that for series as well. But for now, let's actually just learn about the series. So at first glance, they're all here. These are the guys I'm going to be teaching you about. And it is in a handout that is on the class webpage. This is a direct link to it. But if you go to the class webpage and you scroll all the way down to the bottom where it says documents, there will be a PDF document there entitled series tests or whatever. So if you click open that, you will see this table in there. So it's already there. So this is just at a glance. This is the summary. This for our series is going to be the basic rules, quote unquote. So these are going to be like our basic rules for series, which at this point, it looks really hefty. It looks like a lot of information here. And if you've never seen series before, I'm sure it looks quite confusing, but we're going to go through this line by line, one by one. And by the end of the next class, you should be pretty comfortable with this table, all the different tests, how they apply, and when to look for which. Don't be too overwhelmed by the table. I just wanted to put them here as a glance, as a summary. So you can always refer to this table. So if you wanted to write down like a formula sheet for this section, which what we're going to talk about is going to cover sections 10.2 through 10.6. If you want like a formula sheet for that, this table is it. So this table pretty much will cover those four to five sections. Okay, so we're going to go through this table one by one. I'm probably not going to get to all of them today. I'll probably end up somewhere around the comparison test or the alternating series test, but we're going to kind of try to go through as much as we can, and we'll finish up the rest on in the next class, as well as I'm going to summarize and tell you when you would choose which. Although this table also includes a when to use. So there you have right there. There's already also kind of the strategy built into this table, which is why it looks a lot heftier than it is, but we're going to get there. Now, for the convergent telescoping series, I skipped that. There's only one other series that behaves like a telescoping series. It turns out when a telescoping series converges, you can actually determine exactly what it converges to. So just like how last class, yesterday, we figured out that 1/2 plus 1/4 plus 1/8 plus ... added up to the number 1. I could specifically tell you that it adds up to 1. With a telescoping series, I can specifically tell you what it adds up to. This is also true for a geometric series, right? So if I have a geometric series, it's right here, the first row. I can also tell you exactly what it adds up to, and we're going to get into that. But these are the only two tests where you can, in general, tell exactly what things add up to. For the most part, all the other tests, they can just tell you that the series converges, but they can't necessarily tell you what it converges to. We're going to need a lot more machinery to figure that out. Okay. All right, so let's actually just jump in. I'm going to do the test for divergence first. It's actually the second row, but I think that's a nice place to start. One reason why I like starting here is because this is kind of like the most basic. It's almost like an integration by substitution. It's going to be one of the first things you look for. It's going to be like a basic rule or an integration by substitution. It's going to be one of the first things you look for when you look at a series to tell whether it converges. Okay, so this is called the test for divergence. I think at the moment I can make this a little bigger. Okay, so I think we're fitting in here. Okay, so this is the test for divergence, the first series test. Yay! Okay, another name for this is the divergence test, or the nth term test, or the kth term test, or the limit divergence test. But test for divergence or divergence test is how you're going to think about it. So now, as its name suggests, this is a test that's going to tell you about divergence. I want you to recognize that it cannot tell you about convergence. It can only tell you about divergence. So that is something that is important. I don't remember if I typed that in the notes, so let me make it clear here, as the name suggests. It will only tell you about divergence. Okay, So you can't use the test for divergence to tell me a series converges, right? So you would use the test for divergence if you want to show that a series diverges. And it's actually remarkably easy to get this to work. All you need to do is to check that this limit of the sequence term goes to 0, does not go to 0. That's a not equal. If that's true, then it turns out the series diverges. So remember, for a series, we're adding up an infinite number of terms. Let's say that if the infinite number of terms I'm adding up don't get smaller and don't get so small that eventually it's like I'm adding up nothing, the sum is going to diverge. We know that a sum is going to converge if I can add up an infinite number of terms and get a nice answer. If the terms get too big, or if the terms remain too big, I'm never going to get a meaningful answer. It's going to go off to infinity. So the test for divergence takes that into account. If the limit of the terms does not approach 0, the series diverges. And that's pretty much it. That's the test for divergence. Pretty easy. That's the statement right there in the box. You can take a picture of that. We're just going to jump into some examples because there's nothing really else to say right here. So here are a bunch of series, various formulas, probably look quite confusing, but we're going to dissect these based on the test for divergence. Okay, so let's look at the first one. Here's a series, right? So I'm summing up all the terms that look like this. Now, you don't need to really know this, but because we just learned about series, let me mention, this is really something like, well, it's technically I should make that start from 1 because 0 to the 0 is undefined. So this looks like 1 to the 1 power over 1 factorial plus 2 to the 2 power over 2 factorial plus 3 to the 3 power over 3 factorial plus dot, 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 right? There's this infinite sum. I'm adding up an infinite number of things that look like that. And I'm going to forget, so let me fix that. The denominator is okay, but the numerator is not okay. All right, so how would I know whether or not this converges based on the test for divergence? Well, here, notice that my an, if I take the limit of an, that's just going to be the limit of n to the n over n factorial. And what is that limit? That's for you guys. What is that limit? Infinity. Good. So remember, that comes from what we remember about limits from before. Did I touch on that over here? I don't remember. So this thing, we're using this idea right here. So n to the n is much larger than n factorial, as you can see here. So the numerator is going to overwhelm the denominator, and that limit is going to
Jhevon,
go. Yes?
we'll go back to the other page, like the one with the same problem with the n to the n power over n factorial, and
Yeah.
this, you see, this is the same problem. Scroll a little up. This is the same problem. I mean, like, if
This is
it's
the
the
other way
same
around, though.
if it's the same problem, I mean, like, doesn't it converge, by the way? Because it converges to 0.
No, it does not converge, and there are two reasons why. The first thing is, this is upside down. This is not our problem. The problem we're looking at is the series of n to the n divided by n factorial. So it doesn't go to 0, it goes to infinity. So that's the first thing. The second important thing is that, as I mentioned here, it can only tell you about divergence. It does not tell you about convergence. So no, you can't conclude any convergence. Even if the limit was 0, you cannot conclude convergence. So here, this goes off to infinity. Infinity is many things, but definitely it's not 0. So I'd be able to say the series diverges. And we normally say how we know, and we can say by test for divergence. And I put that down because the chat box was in the way, but now it kind of looks weird. Move it up here. Boom, that's it. I take the limit of the guy and notice that the limit did not give me 0. This basically means that the series diverges. In other words, the terms are just too big. It's not going to add up to anything meaningful. All right, what about this one? So here, I look at that. Looks like a very complicated series. Geez, how are we going to know what happens to this guy? Oh my God, you know, here you start freaking out. What did Jhevon do in class again? You're going to test freaking out. Well, what you can do here is look at the limit of an. This is going to be the limit of 5 minus 7n plus 3n cubed divided by n cubed plus 2n plus 1. What is that limit? Quickly. It's 3, ratio of leading coefficients. We, of course, remember that from our limits from Calc 1. And so, in particular, that's not 0. The series diverges. By divergence test. Okay, there we go. Not so bad, not so bad. Let's try this one on for size. All right, so again, I see this. I'm going to look at the limit of an. This is going to be the limit of the absolute value of the sine function. What is that limit? Anyone? Bueller? Infinity? No. 1? No. 0? No. Or are we just now randomly guessing? What are we doing here? Pi over 2. We're just,
Wouldn't
let's
it
guess
just go
all the
between
numbers that I
0
know
and 1?
associated with sine. Huh?
Wouldn't it just go between 0 and 1?
Okay, but what would that mean for the limit?
To be honest with you, I gotta tell you one thing. So if you were to plug in infinity for sine infinity, you would get infinity. And limit of
No, sine of
infinity is
infinity is
infinity.
not infinity. Sine is always less than or equal to 1. It's not going to get anywhere close to infinity. However, it does not exist would be the answer. That's the only appropriate answer, not
Well,
infinity.
what I would say is that it diverges generally, doesn't it? Diverge?
Yeah, but you'd have to know the limit. You'd have to base that on the limit. Now, why is it does not exist is probably the question. What would sine of absolute value of x looks like? Remember, absolute value just means it turns all the negative parts positive. So you'd have like the sine, but instead of dipping underneath, it stays on top. So this graph just bounces like that, right? And it bounces like that forever in both directions. So it never settles anywhere. So the absolute value is going to take the negative part that would have been here and flips it up to the positive part. That's what the absolute value does. So normally there would be a negative part here, but the absolute value flips it up. So now you just have this function that's bouncing up and down. Its maximum height is going to be 1. Its minimum is going to be 0, but it's not settling anywhere. It's bouncing up and down, and it's going to bounce up and down forever. So it does not exist. In particular, D and E means it's not 0, which means the series diverges. Being continuous is not the thing that's the issue here. The thing is the y value doesn't settle. So remember, the limit is what the y value approaches as n approaches infinity here. So the y value doesn't approach anything. The y value just bounces up and down. It's continuously moving between 0 and 1, and it never stops or settles anywhere. So the limit does not exist. Okay, here's the last one. Last example here. Okay, so here I would, again, find the limit. This means that the limit of an, that's limit of 1 over n, right? Fahim beat me to even the question. That's what I would like to see. Answer before I ask. Did you guys see that stand-up? I forgot what the guy's called, but he had this, he was talking about how everyone is so impatient now, and eventually instead of Amazon Prime, they're gonna have Amazon before. Like, send me the stuff before I order it. I want to know. I want you to deliver it to my house before I order it. Same day delivery is not fast enough. Okay, but yeah, Fahim answered the question before I even asked the question. That's what I want. You should anticipate. You know what John's gonna ask me about this? Here's the answer. The answer is 0. Okay, so what does this mean? So what can I say about the series?
Doesn't it converge actually? Because, you know, anything 1 over n, and if you plug in infinity, you would get 0.
I like, converge is wrong. Here's the thing. I like how these, how Kayla and Abdullah phrased it. Very, very lawyerly. Well, we know it does not die.
Yeah, because you introduced to us absolute and conditional convergence.
Okay.
So that's why I said it does not diverge, because
however,
divergence
if you say it does not diverge, you're actually saying it converges.
Yeah, we are saying converges, but we don't know if it's absolute or conditional.
Oh, well, I'll do you one better. It's neither. No conclusion.
Oh.
Remember, test for divergence it only tells you about divergence. It cannot tell you about convergence. Let me make that. It cannot tell you about convergence at all.
Thanks for the note.
Yeah, bruh. That's exactly what I'm saying, as Abdullah said. Okay. So yeah, I mean, I asked that question and I paused here because I knew a bunch of people were going to say converge, and I'm not just doing it to laugh at you. Okay, maybe that's like 5% of the reason. But really, what I want to bring across here is it's a very common mistake. A lot of students think that if they just look at the limit and it goes to 0, that it converges. This is not true. In fact, this series is a very famous series. Does anyone know what this is called? Does anyone have seen this series before? Heart been broken so many times. Does anyone recognize what this series is? This is actually a very famous series. It is what's called the Harmonic Series. So remember how in yesterday's class, someone mentioned something about a harmonic sequence. There is no such thing like that. What there is a series. There's a harmonic series. And so, yeah, this leads to an important fact. The converse of the divergence test is not true. Meaning, if the limit is 0, it does not tell you anything. I.e., if limit of an equals 0, gives no info in general. So you cannot tell. In fact, this guy here, what I mentioned, is actually a very famous series. The series from 1 to infinity of 1 over n. This is 1 plus a half plus a third plus a fourth. It's known as the harmonic series, and it is known to diverge. This actually diverges for sure. However, the test for divergence doesn't pick it up because just knowing that the limit is 0 does not give you enough information. If you're curious as to where the name, the harmonic series comes from, it is actually connected to music. And because there is something called a harmonic series in music, I think it's usually in like stringed instruments. And there are some articles I put over here on that in case you're interested. But yeah, it's true that if a series converges, then the limit will be 0, but the limit is 0 does not mean it converges. So that's very important, right? Another famous one is this series, 1 over n squared. This one is known to actually converge. However, we don't know that by this test. This equals 0 here. Can you guess what this guy converges to? Like if I take 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, if I'm adding all these fractions, someone give me a guess as to what it's going to add up to. 2? Very reasonable, very reasonable. It's not 2. Any other guess? 1.5? Yeah, all right. No? Well, it adds up to pi squared over 6, right? Obviously. Okay, so are we getting an appreciation here for figuring out what series converge to and figuring out that they converge? It's actually a lot trickier than you would think. Okay, however, the first thing I spoke about, the test for divergence, can tell you when something diverges. It cannot tell you when it converges. So if the limit is not 0, I automatically know that it diverges. However, if the limit is 0, I need more information. I need another test. So I obviously put this example in here to kind of fool you guys into realizing that, hey, here's a common mistake. Look out for it. It's not good enough that the limit is 0. The limit is 0 is a necessary, but it's not a sufficient condition. Okay. Harmonic series. First important example. This is a series that actually has a name to it. So it's something you'd want to remember. The harmonic series diverges, even though the limit of this thing approaches 0. The limit of 1 over n squared also approaches 0, and this one converges, which means you can have both convergence or divergence when the limit approaches 0. So just looking at the limit does not give you any information. Okay. So let's move on to the second test. So that was test for divergence. That's it. Look at the thing that's beside the series. Does the limit go to 0 or not? If the limit does not go to 0, you know for sure it diverges. If the limit goes to 0, you don't know anything, right? You have to do some other test. All right. The next test we're going to cover is actually the first row of the table. It's called a geometric series test. Now, the name comes from the fact that it's the sum of a geometric sequence. Now, a geometric sequence, let's see if I can, no, it's, so a geometric sequence is just a sequence that looks like this. It looks like AR to the n minus 1 if I start my n from 1. It also looks like AR to the n if I start my n from 0. Why is it called geometric? It has to do with the geometric mean of numbers. If you're curious, you can look at that link to see where the name comes from, but you don't need to know. Basically, this just means, and I wrote down what the terms look like here. If I sum the terms of a geometric sequence, I get what's called a geometric series. These are series of these two forms. You should know that your A and your R are constants. They are constants. That's very important. I did mention that here, but that's going to be something that, oh, whatever I did, undo. So I did mention that here, but that's going to be something that students are going to overlook and not pay attention to. A and R are constants. A, R, they're not zero, are constants. It's very important. So for example, the series 3 times 2 to the n is geometric. But something like the series of n times 2 to the n is not. Right? That's because the n is in the A position and it's not a constant. Okay? So it's very important that the A and the R are constants. Okay? Now this is what it would look like if you add up all the terms. The A is called the first term and the R is called the common ratio. But this is what it looks like. A plus AR plus AR squared plus AR cubed plus AR to the fourth, etc. So it's like you start with a number A and you keep multiplying it by another number R, and then you're adding all these terms together. This generates what's called a geometric series. Now, I'm going to tell you how we're going to figure out whether this, you're reading the story? Well, I'm going to tell you the story. Okay, so there's a story. We're going to use what's in a story to figure out how these guys converge. There's a story, somewhat of a legend. I don't know how true it is, but I've always heard it. A lot of us have heard it. If you're a math person, you've heard this story, right? So there's a very famous mathematician named Carl Friedrich Gauss. He has a lot of, he did a lot of things in mathematics. He did a lot of things in physics as well, and electricity and magnetism. He did a lot of work in complex numbers, but he's known to be like a prodigy. Ever since he was a very small child, he was studying very advanced mathematics, right? So there's a story, there's a legend of Carl Friedrich Gauss that when he was a young child, you know, 3, 4 years old in preschool or whatever, you know, the kids were just learning how to count with like pebbles and stuff, and they didn't understand the concept of a negative number. You know, he was that young, right? So he was in his class. They were very disruptive, kicking up a ruckus. So the teacher was like, all right, everybody sit down, shut up. I want you all to add up all the numbers from 1 to 1,000. Ah, right? So that was the thing. The teacher gave them that's the thing, right? So you have all these 4-year-olds counting on their fingers, trying to add up all the numbers from 1 to 1,000. Does anyone have 1,000 pedals? Pedals to add up? Right. So the teacher thought that was it. Yeah, these kids are going to be silent for the rest of the time. However, little baby Gauss figured out the answer within a couple minutes, gave it to the teacher, and he was done. Legend has it his classmates are still working on the problem. I'm kidding. I don't know. I just thought it would be funny to add that part. So he just like a boss walks up, here's the answer, teacher, and then he just goes about his business, right? Everyone else is trying to figure out, you know, counting they're taking off their shoes, trying to count their toes and stuff. He figured out the answer very quickly. How did he actually do it? Well, legend says Gauss actually figured out a very important thing. Here is how he actually did it. Well, he was like, all right, I want to add up all the things from 1 to 1,000. And at this point, Gauss was pretty good with algebra by this age, according to the legend, right? So he just wrote down this, and he says, okay, that is the sum that I want to find. That's S. Here's something that he noticed. If I turn the numbers around, there's commutativity of addition. So that's actually going to be the same number. He says that's also S. Then he started to notice, well, if I add these two, I would get 1,001. If I add these two, oh, look at that, I get 1,001 again. If I add these two, I get 1,001. I keep getting 1,001. Notice that he actually added the number twice. So then that's 2 times the number he wanted. How many 1,001s were there? Well, there are thousands of them. So there are 1,000 1,001s. And that is 2 times the sum that he wanted. So basically, to figure out the sum, your S is equal to 1,000 times 1001 all over 2. That is just 500 times 1001. Of course, anyone who's able to figure this out is already capable of multiplying. So he simply multiplied 500 times 1001. And I believe the answer is 500, 500. So it's like, here you go, teacher. It's 500,500 is the answer. Boom. He was done in a couple minutes, right? So that's the story of Gauss. Now, you guys might have seen this. Yes, it's a recap. You actually also did this in Calc 1. So it's not just a recap from pre-calc. It's actually a recap from Calc 1. You actually used it to prove this formula. Remember the sum of the first n terms? You can actually do this in general. You could actually figure this out by realizing that you wanted to add 1, 2, 3, all the way up to n. Then you turn it around, n plus n minus 1 plus all the way down to 1. This ends up meaning that 2s was equal to n times n plus 1, and then your s was equal to n times n plus 1 over 2. So you actually did prove this in Calc 1 as well. At least I did with my class. So yeah, you use this to figure out Riemann sums by the hard way, with the series way. This is before you learned about antiderivatives. You needed all these formulas from series to compute the integral. So yeah, this is a trick. We can actually use a very similar trick to figure out what a geometric series adds up to, it turns out. So we can recall that a series, we can just realize that if we just look at the partial sums and take the limit of that, this was something that I mentioned in last class, that can tell me what a series would add up to. So this means I'm going to look at the partial sums of a geometric series. Add up the first n terms of a geometric series. That means I'm going to add a plus ar plus ar squared plus ar cubed plus ar to the n. And I mean, technically this is n plus 1, but you get it, it's the same. Here, notice that you're going to tweak it a little bit, so it's not quite the same thing, but it's very similar. If you multiply this by r, you're going to get ar plus ar squared plus ar cubed plus ar to the n plus 1. Notice that it's very similar to the previous line. In fact, what we're going to do is we're going to subtract one line from the other. Notice that if I call this line 1, instead of doing what Gauss did and adding the two lines, we're actually going to subtract them. I'm going to take line 1 minus line 2. So on the left side, I would get 1 minus r times the Sn. And then that's going to be a minus this, so there's going to be an a. Then there's going to be the ar, subtract the ar squared, subtract the ar squared, the ar cubed, subtract the ar cubed. And this is going to keep going until this guy is going to subtract the guy right before that. And then I'm going to have minus ar to the n plus 1. Then what I can do is I can solve for the nth partial sum. There's a common factor of a, and I divide that by 1 minus r. Now, the sum, n goes from 1 to infinity of, say, ar to the n minus 1. That's simply going to be the limit as n approaches infinity of this guy. Okay, now what is that limit? Can anyone see what that limit is? At least, can you tell me when it's actually going to make sense? Now, of course, what you need to focus on is this guy right here. See, everyone else in that expression is a constant. The only guy that has the ends in it is that guy. So now you want to know, how are you going to control that guy? What has to happen in order for this guy to actually make sense? Now you can think about this for a little bit. Does anyone see the answer right away? Like what do we need to get this guy to work out? Okay. So now you can think about the values of R and how it's going to behave, right? So you're raising something to the power n. Obviously, if your R is 0, that's going to work, right? You'll actually add up to R. But we know that our R is not 0. Okay, so it's not 0. What can it be? Can R be 5? Well, if I have 5 to the n, that's an exponential function. That's going to go off to infinity. Can it be 2? Oh, still exponential. Can R be 1? Well, I'm going to divide by 1 minus R, so no, it can't be 1. So what if it's bigger than 1? Well, if I take a number bigger than 1 and raise it to a positive power, I keep getting bigger and bigger numbers the larger the power gets. So now I'm thinking, okay, so it has to be smaller than 1. So it has to be like a half. If you keep raising a half to a power, you keep getting smaller. And we can keep going. And you can also realize, if I took negative a half, the same thing will be true. If I take negative a half and I raise that to a power and I keep raising that to a power, that eventually goes to 0. It keeps getting smaller, minus a half times minus a half times minus a half forever. It keeps getting smaller. So basically what we realize is that if our R is smaller than 1 in absolute values, then this part is going to go to 0. Then the R to the n plus 1 would approach 0. And so we are going to end up with A divided by 1 minus R. And it diverges in other scenarios. In fact, since we have absolute values around the R, this gives absolute convergence. So not only can I talk about convergence, I know it's going to converge absolutely. Whenever a geometric series converges, it will converge absolutely. It does not matter if the A or the R are negative. As long as my R is in magnitude smaller than 1, then raising R to the nth power and letting n go off to infinity, this sum is going to actually make sense. This leads us to the geometric series test.
Jhevon, what I was going to tell you is that anything R less than 1, it converges, and R greater than 1, it diverges.
In absolute value. So
Absolute
in other
value?
words, your R needs to be between minus 1 and 1. So your R can be any number in between minus 1 and 1, if you wanted to flesh that out.
I'm talking about when it converges or diverges. Anything less than 1, it converges. Anything greater than 1, it diverges for geometric series tests.
Anything less than 1 in absolute value converges, yes. Anything greater than 1 in absolute value will diverge. Right. And moreover, it's actually converges absolutely. So you actually get absolute convergence for free in this test. There are a few tests where you get absolute convergence for free. The geometric series test is one of them. Whenever a geometric series converges, it converges absolutely. And in fact, by this calculation above, which I found it by the limit of partial sums, I know exactly what it converges to. It's going to converge to this number specifically, A over 1 minus R. So that is a geometric series. So it's a series that looks like this specific form. It's a series that has a very specific form. You need to know what you're looking at. So the test for divergence works on like any series. However, the geometric series test works on a specific kind of series. It has to look like a constant times some other constant raised to the nth power. Okay, now let's actually do some examples. This is going to be the first one. And then we're going to do these. So first one's probably the hardest, so I'll take this one. Don't worry, I'll take one for the team. I'll do the first one. You guys can do the other ones. All right, so here's a series. By the way, this is actually a familiar guy. We actually know the answer to this. We're actually going to see a different way to do it now. Notice that this is a half plus a quarter plus an eighth plus a 16th plus dot, dot, dot. This is that old dichotomy paradox sum. We already know what this guy adds up to. We actually know the answer is 1 already. Now you can compare what I'm going to do here to what we did yesterday, but we actually know that this converges. Let's see if we can figure out that it converges some other way. It turns out that it is actually a geometric series. Notice here, note, this is the sum. I can look at this as a half times a half to the n minus 1. Okay, so remember, in other words, to apply the geometric series test, and you guys should probably take a picture of this box, the geometric series test box. To apply the geometric series test, I have to have two very specific forms, one or the other. If you want to know what the difference between these two forms are, it's from where the series starts. If it starts from 1, then I have to start the power at n minus 1. If it starts from 0, then I start the power at n. Basically, the geometric series has to be the form where the a is going to be the first term. It has to start with a plus ar, then ar squared, then ar cubed, right? So it has to be one of these two forms. Because this one starts at n equals 1, I know I want to write it to look like this form right here, a times r to the n minus 1. So notice that 1 over 2 to the n. I can just think of that as a half raised to the nth power. And then by laws of exponents, I can factor off one of the halves to get a half times a half to the n minus 1 power. Now this guy here, the half is my a. And this half here is my r. So this is in the form ar to the n minus 1, and the sum n goes from 1 to infinity. So that's the form that I'm looking at. So now I recognize this as a geometric series. How am I going to recognize it as a geometric series? Well, it's going to be something specific that you're looking for. We'll look at strategy later. But for now on, just notice that this is a geometric series. I can write it in this form. So what does this converge to? So the series converges absolutely. In fact, I know what it converges to. It converges to a over 1 minus r, which is a half over 1 minus a half. Well, that's just a half over a half. And look at that. It's actually 1, the answer that we got before. It converges to 1 by the geometric series test. So this series actually converges. In fact, it converges to 1. Now that is something that we figured out yesterday, but here's just another way to do it. It turns out that the series that was in the dichotomy paradox is actually a geometric series. I could have noticed that these guys would have added up. I took a half, which is like my first term, and I keep multiplying by a half. Multiply a half by a half, I get a quarter. Multiply a quarter by a half, I get an eighth. Multiply an eighth by a half, I get a 16th. I keep multiplying by a half. So this guy is actually a geometric series.
Jhevon, actually, isn't the A supposed to be like 1? Because rather than
No, the A does not have to be 1. The A has to just be a constant.
constant.
Yeah, it does
So
not
why
have to
doesn't
be
it
1.
converge to 0 rather than 1? Why doesn't it converge to 0?
Well, we showed earlier that this is what it's going to converge to. That does not go to 0. Now, for sure, the sequence converges to 0. If I look at the limit of 1/2 to the n, that goes to 0. But remember, the limit of that going to 0 doesn't mean anything. The sequence converging to 0 doesn't mean the series converges to 0. These are two very different things. So this series actually converges, but it converges to 1. The sequence that it's summing converges to 0, but it had to converge to 0 in order to converge. So yeah, that's the geometric series test. Here are some more examples. All right, it turns out that this guy is actually, you can use this geometric series test to solve this guy. I'll give you guys some time to think about it. I'll give you guys like 3 minutes. Try to figure out if this converges, tell me that it converges, and then tell me if it converges, tell me what does it converge to. I'll give you guys 3 minutes. Go. All right, about 30 more seconds. Some people are probably like, dude, you could give me all day. You can give me 30 more hours and I wouldn't know what's going on. But actually try.
Do you please go up to see what the geometric series formula is? like, earlier, like, in regards of 1 minus r, like earlier a parentheses 1 minus something, like maybe let's go a little
Oh,
bit
you
up.
don't need that. That's not what you need to focus on. You need to focus on what's in this box. This box has everything you need to know. This is actually deriving what we have in this box. Dawa has a suggestion. She says, thinks it converges to e over 4 minus e. She's like, she's absolutely sure. She's like, fight me if you disagree. I'm kidding. She's like, okay. So Dawa thinks it converges. Does anyone else agree? Anyone else have any input at this point? Do we think it converges? Is there anyone who thinks it diverges? Anyone thinks it converges?
Converge.
You think it converges? What's your A and R?
R is 1 over 4. And the A is kind of a tough one.
Okay, so Dawa thinks it's e to the 4 and e to the 4 respectively. Your A, both your A and your R are e to the 4, e over 4. Okay, so this one is a little bit tricky because there are actually 2 R's and 2 A's. You see that 1 plus e to the n in the top is kind of hard to actually deal with. So what I would do here is I would split it because the e is raised to the nth power, but the 1 is not. And it's not 1 plus e all to the n. So this kind of begs to be split up, actually. And we can do that by the properties of series. So now the goal is to write each of these as a geometric series. Okay, so what about the first one, now that I brought it there? So from the looks of it, Kayla, your answer only works for one of them, not both. So now remember, in order to know how to apply the formula in the geometric series, I have to write in the specific form to identify the A and the R. Notice here, because I start from n equals 0, I want this to look like a constant times some other constant raised to the nth power. Here I have the 4 raised to the nth plus 1 power. So that's automatically something I'm going to want to fix. So I'm going to write this as just factor off the 4 and write this as 1 over 4 to the n. Of course, this can look like 1 over 4 times 1 over 4 raised to the n, as n goes from 0 to infinity. And that, for the first one, my A is a quarter and my R is also a quarter. I can do the same thing for the other guy. First, I would factor off the 4, and I'd be left with e to the n over 4 to the n. That means I can rewrite this as a quarter and e over 4 all to the n. So here my A is a quarter and my R is E over 4. So that was Kayla's answer. However, she left this guy off. Okay, so now, do these guys converge now that I wrote it like that? So remember, when we want to determine if these guys converge, we have to look at the R. Is the R in absolute value less than 1? So if I take a quarter and I put it in absolute values, do I get something less than 1? For sure. If I take E divided by 4 and put it in absolute values, is that less than 1? So remember, E is 2.7183, right? So E is less than 2.8. So this is like 2.8 divided by 4. Yeah, that's less than 1. So both converge. In fact, both converge absolutely. So in fact, these both converge. This one converges to A over 1 minus R, plus the other one converges to A over 1 minus R. So this converges. I can multiply top and bottom by 4. That would look like, so if I take this and I multiply by 4 over 4, that is going to look like 1 over 4 minus 1, 3, plus, I can do the same thing here, multiply this by 4 over 4, and this is going to look like 1 over 4 minus E. So that's the answer. The series converges. In fact, it converges absolutely. Yeah, I think it's beautiful too. Absolutely to this. Look, Ma, I just added up an infinite number of numbers. You want to know what the answer is? How can you do that? Look, my son is in class still trying to add the numbers from 1 to 1,000. How did you add up an infinite number of numbers? Oh, I just did what Gauss did, Mom. Yeah. So yeah, we just added up an infinite number of things in a very short span of time. Yes. But again, the splitting up is very important because the splitting up allows you to write in either one of these forms. Before splitting up, I couldn't get it in that form. So that's very important, right? Notice here, I could not write this as a constant times something to the nth power, right? I mean, how would you even try? I can tell you a common mistake that some students would make here though, like especially if I'm like writing a multiple choice test. A lot of students are going to think about this in their heads like that. If not, for sure, write it down. And then they're going to be like, oh, so this is like 1/4 times 1 plus E over 4 all to the N. And so that's my A and that's my R. But this is actually a distribute power across sums mistake. That's a blasphemy. But I can tell you it's very common. Students will tend to do something like that or something very similar to that, where they just kind of think of the N as affecting the 1 as well. Some people might merge this in their head, the plus sign, and they just think of that as E over that. So a lot of students, another common mistake, some students might merge this in their head. They might think of this as E to the N over 4 to the N plus 1, and then they would write it as 1 over 4 times E to the N over 4 to the N. And so they'll get their A is 1/4 and their R is E over 4. So that's another mistake that could happen, very common, but both of those are actually incorrect because it's a mistake in algebra. However, if I split them across the sum, which I know I can do for series, then each individual actually behaves geometrically. So a part of this just comes from knowing how the algebra is actually going to work out. A part of it just comes from experience. You practice a few of these, you're going to see little tricks like, oh, if I split this up, this is what I'm going to have. And if I keep this together, that's what's going to happen. And I can split this up, and this part over here is geometric, and this part over here is a different kind of thing. But eventually you'll be able to actually see these things. But this one, splitting it up, was the golden ticket. And it's actually a sum of geometric series. Yes, never made that mistake. Yeah. And I suspect Kayla made a similar mistake to that as well, but I'm not gonna like blow up her spot. No? Okay, good. Are you saying, nah, you don't care if I blow up your spot, or are you saying, nah, I didn't make the mistake? Okay. All right, this one's a little bit easier. Maybe someone can tell me in 30 seconds. It does sound like the form. Maybe someone can tell me this one. Does it converge? If so, what does it converge to? Or at least tell me, pleading the fifth, at least tell me what the A and the R are. A is 1 over pi, E is R is E over pi. Wait, hold on. I didn't say where that started from. Did I miss that, or was that deleted? It actually is important where it starts from. I don't know where that went. Maybe 0. Does that change the answer? You didn't even notice that I didn't have the starting point? It's actually important. So if the starting point is missing, you should notice. And you should say something. Because starting at a 1, starting at a 0, they're very different. Starting from a 0 means I want to write things to the r to the power n. If it started from 1, I'd want to write it the r to the power n minus 1. If it started from 3, I would have to write the r to the power n minus 3, etc. So yeah, so what I would do here is, because I see the n equals 0, I know that I need to write it to the nth power. So I can factor off a pi here in the denominator. In fact, I can factor off an e over pi. And this will leave me with 1 over pi to the n. The e does not have the power n, so this is that. Okay, so now you see that the a is the e over pi, and the r is the 1 over pi, and Dawa got it. Let me make sure that this wasn't. Did I leave it off over here too? Yeah, it was a typo. It was missing the whole time. Just throw in a 0 there. So there we go. And so now 1 over pi is less than absolute value. Since 1 over pi is less than 1 in absolute value, the series converges. In fact, absolutely.
Do you think that the answer is e over pi minus 1?
Right, so it converges to a over 1 minus r. I don't know. Let's actually see. So that would look like e over pi divided by 1 minus 1 over pi. And I would multiply that by pi over pi. And so it would look like e divided by pi minus 1. Was that what you said?
E over pi minus 1.
Yes, that's correct. So that's what it converges to. So that's a geometric series. I believe there was another one. Okay, maybe a minute on this one. Turns out that that guy is a geometric series. Determined if it converges, and if it does, let me know what it converges to. If you think you know what the A and the R are, you can also let me know that in the comments. Or I guess you can maybe say it. Okay, ideas. Does this converge? It's actually geometric. What is the A? What is the R?
I'm assuming a equals 1 and r equals negative 3 over 2, and how you would solve is 1 over 1 minus negative 3 over 2, and you would get 2 over 5. That's what I'm assuming.
Okay, you started off great, but you messed it up at the end. Think about what you just said, though. Your A and your R are correct. So yeah, A is easy when it's written out like this because it is the first term. So that's your A right away. So now you have to figure out what is it being multiplied by. So that's your 1. Then it's plus, you have to have a 1 times, well, it's going to be minus 3 over 2. Plus, then you have a 1 times minus 3 over 2 squared. Plus, you have a 1 times minus 3 over 2 cubed. That's what you actually have. Now, of course, this manages to alternate the signs. Here's going to be negative, here's going to be positive, here's going to be negative. And yeah, you can think of this as a minus 1 to the n, as some people were saying in the comments. You don't necessarily have to do that, though. We're going to talk about series that have that component to it. But right here, I can just immediately jump into the fact that this looks like 1 times minus 3 over 2 raised to the n. N goes from 0 to infinity. And yes, this is equal to, I could think of this as minus 1 to the n, 1 times 3 over 2 to the n as well. But here, that's a little bit more complicated than I'd want to think about it, but it is actually true. You can just alternate the signs with a minus 1 to the n. However, here, the A is 1, and the R is minus 3 over 2. Okay, which is what Jason said. However, what is our conclusion? The conclusion was actually incorrect, Jason. Do you see what the mistake was?
A is 1, and the R is -3/2. And you
Yeah.
know, when the formula, geometric series formula is A over 1 minus R. So I'm assuming since A equals 1 over
No, no,
1
no. When you're missing, when does that formula actually apply? That's the issue.
absolute value. I don't know.
Come on, Jason, don't say that. It's not true. Look at the box. Remember this box? The box has everything you need to know. So here is the form, and it says the series converges absolutely if there's a
R is less
condition
than
on it.
1.
Not less than 1. R is less than 1 absolute values. Their absolute values are on this. Right? Which means if I put the R in absolute values, that thing needs to be less than 1. Now here notice that the absolute value of R is the absolute value of -3/2. Well, that is +3/2, and that's bigger than 1.
Diverges?
So it turns out that that formula does not apply. It's greater than 1 in absolute values. This means the series diverges. It's geometric, but it diverges. Geometric series test. So what I put in a box is pretty much all the information is actually pretty important. That's why I put it in a box. And if you look in the table, the original table that I gave you from before, this also tells you specifically that it converges when your R is less than 1 in absolute value, and it diverges if your R is greater than or equal to 1 in absolute value. So these little things, those little pieces of information are also important. So yeah, plot twist. Like all of them were converging except this last one. I knew you guys would get too comfortable with the convergence, but a geometric series can diverge. It will diverge if your R is greater than 1 in absolute value. So that was an example there. Did I have another example? No, that was it for geometric series examples. Let's talk about one other test. There's only one example for this one before we get out of here. And I'll probably also make an announcement. There's a test called the integral test. Now this can actually work on any series potentially. So here's the thing with the integral test. You're looking at a series. If it's equal to 1, it diverges. It has to be strictly less than 1 in absolute values. So if you go to this table, which it'll be in the notes, and there's a copy of this table on the class webpage as well. Notice in the second line, it says diverges if absolute value of R is greater than or equal to 1. So equal to 1 is also bad. Right? And we could tell that from the proof. If your R is equal to 1, you're dividing by 0. Like that's not gonna be good. Limit's not gonna exist in that case. So the integral test is the last thing. So integral test, how does that work? This works on any series in general. It doesn't have to have a very specific form. However, it's going to be a form where you kind of notice that you can integrate things easier. So if you can look at your an as a function and look at that as a function and then compare this to an improper integral. So here's somewhere we're going to need improper integrals. Then what can you actually say? If I, instead of an, I think of it as a function and I'm integrating from on the limits. This means, well, I can imagine that there's some function and it's decreasing, of course, because I want the limit to go to 0. So if I look at the area under this curve, going on forever, the area here, the area of that is going to be equal to the improper integral of this function. However, if I'm looking at the series only works on the integers. So the series only works on the a, it also works at the a plus 1, it also works on the a plus 2. It only works at certain points. So what you'll notice is that if you replace the series with an integral, the series is actually much bigger. The integral is much bigger in general, at least one version of it. If you wanted specifics, it can kind of get a little bit tricky. But as for some intuition, I want you to understand that it's harder to get the integral to work out than it is to get the series to work out, because the series only counts on these integer values, whereas the integral is taking all the values in between as well. So it kind of tells you that the integral is harder to work out than the series is to work out. So whenever the integral works out, you expect the series to work out. To be a little bit more specific, that's very hand wavy. It's not meant to be a proof or anything. And it's not even 100% correct the way that I just claimed. But just to give you like an intuition or a feel for what's happening, that's how I would explain it. Ultimately, we can end up with this sort of scenario here that we call the integral test. If you look at any series and you can look at the sequence as a function, and the function is continuous, it's decreasing, it's always positive, then the series and the corresponding improper integral will actually both converge or they'll both diverge. In other words, you can tell what the series is doing by knowing what the improper integral is doing. And of course, we know how to compute improper integrals, so this is actually going to be not so bad. It's very important that you realize, though, just like with the geometric series, the conclusion only follows in a certain scenario. This has to be true. So that's actually an important part of the thing. I'm not saying for any random series you can just start integrating instead of doing the series. This is not true. That does not work. The series thing has to be continuous. It has to be eventually decreasing. It has to always be positive. Under that scenario, if you do an improper integral, you can determine what the series is going to do based on what the improper integral is doing. So let's actually look at an example. Determine whether this series converges or diverges. Here's the thing. Note, an equals e to the 1 over n squared. The corresponding real function the chat box is in the way here. Let me move it out of the way. The corresponding real function is, well, f of x equals e to the 1 over x squared. Now, if I look at this function, for x greater than or equal to 1, which is where the series is starting, f is continuous. It's an exponential divided by a polynomial, and I'm not dividing by 0. Also, f is decreasing. How do I know that it's decreasing? Well, I know that it's decreasing because if I look at f prime, that's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This would look like there's a minus e to the 1 over x common factor. That would be a 1 plus 2x over x to the 4th. Now, this part here is obviously always positive. So this tells you f prime is negative. So my f prime is less than 0. This means f is decreasing. So my function is continuous, it's also decreasing. Also on top of that, the function is always positive. So I am now in a situation where my function is continuous, decreasing, and positive. Bonus, where this is particularly useful, f is easy to integrate. So if you look at something and you notice that it's easy to integrate, I would probably start making my mind go towards the integral test. In order to apply the integral test, these 3 bullet points must be fulfilled. Otherwise, the test is invalid. So these have to work out for the test to even be a thing. These 3 things work out for this particular series. So now what I'm going to do is I'm going to look at the improper integral. So now I'm going to consider the integral from 1 to infinity of e to the 1 over x squared. All right, my integral warriors, how do I do that integral? U substitution, right? U equals the power, right? So if you do U equals 1 over x, your du is going to be that minus 1 over x squared. Ultimately, this is going to bring you to a situation where the integral is minus e to the 1 over x between 1 and infinity. And yes, I know technically we're supposed to take a limit as n approaches infinity of 1 up to n of the thing, but you get the idea. Now, if I plug that in, plug in infinity here, I would get 0, and adding and plugging in 1, I would actually get not 1, I would get e. This is going to be 0 plus e. In other words, e. So the improper integral converges to e. Now that's going to be greater than or equal to whatever the series actually converges to. So this means we're running into the other guy here. Move this guy down a little bit. So I didn't mess any formatting up. So that's E. In other words, the integral converges. Which means the series converges. By the integral test. In fact, it converges absolutely. I mean, because it's always positive, you know that it's going to be absolute here. If I put absolute values around it, it's not going to.
Scroll up actually a little bit.
Yeah, so here, just to recap, this is my series. I realize if I think about the sequence term as a function, the function is continuous, decreasing, and it's greater than or equal to 0. This means the integral test is applicable.
So you have u as 1 over x, right? And then du
Yes.
is negative 1 over x squared. So
right.
It says 1 to infinity, like, let me see the, go scroll up, like, it's the problem.
To that?
Oh yeah, 1, I see. So yeah, what I want to tell is that basically I just want to know that how do you got E as your answer, and that's just about it. I just want to check with what are the endpoints.
I mean, if we do the substitution, right? So this would lead us to minus e to the u du, right? Because the 1 over x squared is minus, right? So this means that minus du is equal to 1 over x squared dx. So then this guy, the 1 over x is just u, so that's e to the u. The 1 over x squared is the minus du, so we just get that. The integral of this is minus e to the u plus c. So the integral is just minus e to the 1 over x plus c. However, it's a definite integral, so I have that. Like I just did the integration.
If it was like, from negative infinity to 0, what would the answer be? If it was the endpoints are negative infinity to 0.
You mean 0 to negative infinity? Well,
Negative infinity
that
to
is
0. Negative
You mean
infinity to 0.
negative infinity down here?
Yes, to 0.
Well, in context, that would not happen, right? We don't have series where the lower limit goes down to negative infinity. So we wouldn't be in that scenario here.
But generally, if it was like an improper integral question and it's just asking
Yeah, I
you
would
from
just take a
negative,
limit. I would do a limit. It would be the same thing. So I would have a negative infinity down here and a 0 up there.
yeah, and what would be
However,
the
that
answer
would
then?
diverge. That would diverge because if I plug in a 0 into the 1 over x in the power, it goes off to infinity. So that would diverge.
Okay.
I mean, this is just computing the improper integral. This is something we covered in a previous class, so you would do that. Ultimately here, this integral as is converges, and that leaves us with the answer. So that's the integral test. It's useful when the thing is easy to integrate, but it's only applicable if these 3 conditions are fulfilled. For this example, they were fulfilled. Now, I'll leave the notes for these guys up so you can, if you want, read ahead and try some of these problems. But we're going to stop there for now. Question, if I plug in infinity into that, that's e to the 0. So it's not 0, it's e to the 0. So that's actually minus 1. Yeah. Yeah, I'm rushing to get out of here, making mistakes. Natalie's keeping me honest. All right, we're going to wrap up with that. One thing I did want to mention though, so I'm just going to run this by you guys. I'll post a PDF of the notes online as usual, as when I post the video. So your first test is next week, Thursday. I hope you guys realize that. It's very packed. And under normal conditions, I like to have you guys have a weekend between tests, but for the summer, it's not possible. So technically your test would cover everything we cover up to Wednesday if we are to remain on schedule. And so for you to cover everything up to Wednesday and have one night to study for the test, that's kind of cramped. So I was thinking of something and I wanted to throw out to you guys, and you guys can let me know if this is something that's doable, is what I could do instead. I don't want to push the test into the next week because then that might interfere with, the last day to drop a class and blah, blah, blah. And I want you guys to have more information too early. But what I can do is instead have you guys do the test on Friday. So you get an extra day to study. I'd have a regular lecture on Thursday. You guys can do the test on Friday. So that being said, I know a lot of people have things going on Friday in the evenings, or they might have work. So that might not be able to work. So just to throw it out there, if you can do it on Friday, or rather, I guess what I want to know, if anyone cannot do it on Friday, I want to know if that's possible. But I would probably do it during the day.
Jhevon,
Yeah,
I have a quick question.
Saturdays.
Oh,
So,
yeah.
so
For
Kayla
the,
has a problem on Friday.
yeah. Would it be
In general,
easier to
does
do it on
anyone
the
else have a
weekend?
problem on Friday?
I got to tell you one thing. If it was like, so you know what I thought about Friday's exam in
Yeah.
regards of like, the test of what we learned? I thought it was gonna be whatever we covered up until Thursday, like which is today.
Oh, no, it's gonna cover more.
Or
Like the stuff we're covering next week will also be test material. That's what I'm saying. It's kind of
is it gonna be
cramped, which is
multiple
why I wanted
choice
to.
or short answers?
I think it's gonna be multiple choice
All of
on
it,
the
or
grade
is it
stuff.
gonna be short answers, or both?
Multiple choice.
All of them,
Yeah, pretty much. I mean, if I change my mind, I'll let you guys know, but I'm envisioning all multiple choice.
including like definitions. Is it gonna have like definitions or just problems with multiple choice?
Okay, right now the format isn't important. Right now is when it's going to be. So the thing I want to figure out is would you guys want it to be on another day? And I wouldn't really push it past Friday. Yeah, it's going to be around an hour and a half long.
I have an alternative. Would it be easier to maybe do it on Saturday? Because as you mentioned, there's students that are also working and some people might have other commitments on a Friday. So
Yeah, Saturday, I would be okay with Saturday. The thing is, I know there are a lot of people who can't do it on Saturday for religious reasons. So if there's anyone like that, or anyone who can't do it on Saturday either, that's what we'd know. I'd like to know. Okay, maybe Saturday. Does anyone have a problem with Saturday?
Speaking of the exam that we have, like the upcoming week, it would be nice if we do it like for the week after that.
No, the week after is too late. I'd go with Friday or Saturday, and it seems like Saturday would work. Okay, so I just wanted to feel, so I just wanted you to feel out what it is. I'll send out an email with more information, probably maybe even send out like a doodle poll or something to see when period people can make the most. But you pretty much, I'd like to just kind of know if it was possible because it's kind of going to be cramped. So if Saturday can work, if there's anyone who can't do Saturday, let me know, and we can go from there.
Monday, do we
Anyway, I
have a
just wanted
quiz
to
on
throw that out.
Monday?
Think about it, and we'll pick up with there. But for now, we're going to let out, and I will.
Are we gonna have
You
a
guys
quiz on Monday?
No quiz, right? So because next week there's a test, I'm not going to give you a quiz. Give you a quiz and a test on the same week. What do you take? Okay, so no quiz, just a test next week, and it's going to be from the sounds of it, it's going to be on Saturday, which would give you guys a couple more days to study, which I think is nice. But yeah, as I mentioned, I'll send out an email about this to verify again, make sure that no one has issues with that, and we will stop there. Jason, did you want to meet with me in office hours or?
Well, actually, I thought about it. It was mainly about our, in regards of the quiz and the exams and
Okay, all
everything
right.
like
So
that.
I'll answer all those questions later. So we'll just wrap up. So there's no quiz next week. There's just the exam, and it's going to be on Saturday, it looks like. But I'll verify everything. You guys will know everything ahead of time, and we'll stop there.
You know exactly how many questions?
I'm not going to tell you exactly how many questions, but it's going to be like an hour
I'll
and a
talk,
half
I'll
long.
talk about
You'll
it
have
during
enough
office
time.
hours.
All right. So, all right. I will see you guys. Ciao.